Alright, so hey guys, how's everybody doing today? This is meetup number 5. Is this anyone's first time here today? You guys need, cool, and I've already been over with y'all. Do you have a Windows machine?
Here.
Okay, his Windows machine? Are y'all sharing the same machine? Cool, then he's already installed the driver, you're good to go. So in case y'all weren't aware, we're focusing on IoT topics. This is a meetup series that I'm doing the second Tuesday of every month from 7 to 9 p.m., January through December of this year. This is number 5. Previously, we've covered the embed online compiling toolset, DLE, and then this is our 5th meetup. We're starting a new 3 meetup series, and we're going to be focused on internet connectivity. So this is the first of 3. Today we're going to be focusing on the Berkeley socket model, what it is, why it's awesome, and how it works. Then we're going to talk about TCP and UDP, which are implementations on top of that model. And then if we've got time, we're going to touch on protocols. Any questions, any thoughts, concerns, existential crises? Yeah. So, the internet sandwich. There's a whole bunch of layers in case you didn't know. The layers look like this. You start off on the bottom layer with your physical interconnects. This is your coax wire versus your twisted pair versus your Ethernet versus your Cat6, Cat4, Cat5. It's what the little bits actually came across. And then you start going up the stack and you get to the data link and the network, transport, session, presentation, application. There's a whole lot of information here. Most of it you don't have to care about unless you're getting paid a lot of money by someone to build something new from scratch. So for most purposes, you care about 2 layers. There's the application layer and the data transport layer. These layers kind of break up like this. In the data transport layer and the application layer, 2 different things happen. In the application layer, you write your high-level apps. So layers 5, 6, 7, you can jump between them, you can exclude them occasionally, but in general, they just get lumped together for high-level things. And then your low-level drivers and network interface tend to happen on levels 3 and 4. And levels 1 and 2 are totally hidden from you by the time you hit software. They're implemented in ROM and physical hardware, usually as an ASIC in a router somewhere. So you never know what's happening, it just works for you. There's this thing called the Berkeley socket model, which interfaces with this. The Berkeley socket model takes your data transport layer and your application layer and separates them with a socket interface. This is really important because if you've got someone writing an application, they don't care how it gets to the internet. They don't care what the backend communication network is. They just care that they get somewhere from point A to point B and that their data gets to the device. In the old days, before you had the Berkeley socket model, if you were writing an HTML web page, you had to know how your Ethernet driver worked, how the switch you were running on worked, the different functionalities between all those switches, and maybe if you worked on twisted pair versus coaxial. Can you imagine writing a database or a web page nowadays and having to worry about drivers at that low of a level? It's insane, and you never get anything done because you'd be worried about all this stuff in between. So a couple of smart guys in the 70s got together and they made this thing called the Berkeley socket interface. Later went on to be distributed with the Berkeley socket, Berkeley socket and BSD. They're interchangeable terms for reasons that people with neckbeards debated for years, but they are the same thing. Just trust me on that. The Berkeley socket API is a set of functions. And what it does is allows the people in the top level to talk to the guys at the bottom layer, and you don't care what happens on either side. So if I'm writing a web app or a web server, at the very highest level, I'll say, here are the 5 or 6 functions that I care about. Hardware, go take care of that for me. And whether it's Wi-Fi, whether it's Ethernet, whether it's a satellite link up, it doesn't matter. It just takes it and executes that API for me. So it's this nice little abstraction layer. It's composed of these functions. Any questions so far? Anyone wondering why the sockets are really, really important? Yeah? Okay. So I'll dive into this a little bit more in a second, but you need to know there's 4 basic categories for the functions. There's client-only functions, server-only functions, functions that are used occasionally but aren't necessary, and then core functionality. So every time that you have a connection with a socket interface, you're going to have a client and a server, and they're going to exchange these every time functions back and forth, and you're going to have to execute those. So in theory, if you want to implement a Berkeley socket interface, you have to implement the functions in the every time client and server columns. You can ignore the sometimes function and just hope no one ever calls it. It probably will, but that's how it breaks down. Questions? So it builds on top of the sockets interface, which you should probably not ever have to worry about, is something called TCP and UDP, which is something you will have to worry about. TCP and UDP sit on top of and use the Berkeley socket interface, and they kind of get muddled in with it because they can be called from both sides of the stack. The differences between the two are essentially that UDP is connectionless and sends stuff from one side to the other without a guarantee of transmission. So you go from point A to point B, and you don't know if it got to point B. You're just kind of trusting it gets there, and you keep sending stuff one after another. The good news about that is it's got a really small overhead, because you don't have to care about if the packet got across. You don't have to keep track of state. Your internal state diagram winds up becoming ready, send, ready, send, ready, send, and that's all you're doing. A good analogy for this is like the post office. You send a piece of mail before checking that the person lives at the address, and this is assuming the post office doesn't have return to sender. It just forwards it onto the PO box and never cares if someone's there to pick it up or not at the other end. TCP, on the other hand, guarantees delivery. It will promise you that something will get to the other side. It has session. It has the concept of a connection from end to end, and it has a handshake. So when you send TCP, the server will say, hey, I got that. And the client will go, okay, cool, sending the next thing. So you can guarantee that stuff gets across. The side effect of this is it requires an internal state diagram. It requires more overhead, and usually requires a bigger buffer size, because you have to pool everything together and then bit by bit send it across and get an ACK and send it across and get an ACK. So it tends to be a little bit slower, and the driver tends to be a little bit larger. A good analogy for this is the phone rings, the other side picks it up and says, yeah, I'm here, and then you'll start talking and sending things back and forth. Questions on the differences between TCP and UDP? It's going to be very important you'll essentially remember this later. One last analogy. TCP or UDP is usually used for streaming data. TCP is usually used for connection-based data. So if you've got a video stream, you'll broadcast out. It's like a fire hose. You just kind of point it at the other side and shoot everything across. And if you're fighting a fire, you don't care if 10% falls out and missed on either side and doesn't get across. You still get 90% of what you're intending across. And usually there's an algorithm at the other side that'll correct for that and say, there's a little bit missing here. I assume based on the colors around it, you wanted this. In real world applications, you'll see up to 20 or 30% data loss being acceptable in a UDP stream, because the algorithms that pick it up on the server side are just that good. This is what a socket connection looks like in UDP and TCP. You'll notice that the UDP one is smaller than the TCP one. That's because it's simpler to implement. So typical UDP connection goes like this. Both sides open up a socket. The server binds a socket to a port number, so it says, oh, this internal abstraction, it's going to be listening on port 8080. The client, in this case, will then say, hey, I'm sending ABCD to port 8080 on my server address. So it'll send it across, the server will receive it. It can then optionally send something back or not, and then the connection closes. There's one thing to note, that bind call right here, notice how it says bind optional on UDP. If you want to call received from on the client, you need to bind it to a port. It's kind of like saying the server is a human being and I'm binding it to a port number, which is their address. So if I tell the US Postal Service to send a piece of mail to someone, I need to know their address. Similarly, if I want to receive a piece of mail from someone, they have to send it back to me at my address. If I don't have an address, there's nowhere for them to send it to, it's never going to go anywhere. Because of modern day firewall implementations, if you don't bind a socket, you can't receive. It just bounces off the outside. Good on that? Okay, that's UDP, where binding is optional. TCP, on the other hand, it's kind of required because it has a connection. You gotta get things back and forth. So if you'll notice, there's this TCP diagram. You initialize your socket, you bind it to a port so you can now send and receive data on it. You're listening on that port, waiting for someone to connect. Someone connects to you, and then you go, hey, I know this guy or I don't know this guy. If you know them, you accept the connection, it spins off its own little thread and keeps running. If you reject it instead of accepting it, then it bounces off and you can ignore them ad infinitum. At that point, it becomes a connect, write, read, back and forth. Cool thing to notice, receive from and send to on UDP versus read and write on TCP, they have different names, and that's for a reason. If you look at the BSD implementation, their API, they're very pedantic about this. Send to, read from have different meanings from read and write, and it connects to being a UDP function or a TCP function. And the technical language doesn't really matter, but those can only be used by those protocols. There's also one called send all and receive all, and the only reason that it's different is it does some magic with buffers. So you'll see on this slide how it's got send, receive, read, write, send to, receive from. They're all essentially the same thing. You just use one with UDP, one with TCP, and then one with send large chunks of data versus not large chunks of data. You don't really care. So, that said, before we move on to Ethernet, any questions on TCP versus UDP? I promise we're going to get to examples in just a second here. So, for Ethernet, everyone grab a partner, preferably someone near you. What we're going to do is, using those boards, we're going to go to the embed socket page. Everyone is going to, in the pair, one person's going to load the UDP server, one person's going to load the UDP client. You're going to open up a terminal to each one, and you're going to send data back and forth. Server is going to have to turn on first so that you can get the server IP, and then the client is going to have to compile using that server IP and hook up. Okay? Me and my companion Sam back there are going to be walking around here to help it all out. So, example number one, follow the Google link, follow the instructions. Because we're just smarter, we know how to scale.
I've done stuff without any problems. So what is this one?
So it's like a
So if you're running it in virtual box.
Okay. What's the
I think he is. I think it might be the same thing.
We're just downloading this Google Drive.
It's got a so we import the live.
Do you have a partner? So somebody's.
We can have one server and
Yeah, that probably
so once we've got this, then
Is that Robert? Yeah, it this is really because my kid well, actually, mine are rich. You are out there.
what was your indication?
You don't get that, right?
But that could be an addition, but probably always hard. These are live. You guys agree?
Yeah, the server.
I thought I might have. I don't know. Just start with this.
Have you looked into the server
It doesn't really. I believe you have to connect it to. This one.
How do I?
One is the server and one is the
Yeah, I did that.
So let me know what you have.
Is there like a serial monitor or something?
That's great. Oh, the website.
So I built this on it.
Yeah, it pushes it down.
Yeah, it's gonna print it out. Next page is it'll print it out.
So what you can do, I'm gonna say there's to the board.
Andre's doing okay? Have you set up an account?
Okay, so I need to change that.
What kind of turkey is that?
Talking about like
Money install.
Sort of a serial.
Trying to type in money, maybe it's
Where's it getting the DHC?
do we have to
Yeah, no, I'm thinking that.
I should do
just like the argument ID.
Yeah, and that IP address is not working.
I'm not even aware. I don't know what is it.
I have some.
It might not be configured. I just couldn't get it.
Shit show.
It's so exciting.
Which one you want to be?
You did not leave that. Now we figure out why.
I just imported the server.
So how to check this? What's it wrong? How are we gonna?
Prints out the open up a terminal.
No, that's before I get
How will we even get an IP address?
Oh, yeah, that's right. I was trying to do it.
Connect the switch only, we're not connecting the router.
So there is one thing I forgot to mention. Getting the server address, you get it from the terminal. So if you want to get your main code, there's a printf statement saying server address is blah. It's printing out to the terminal. So open up a terminal to it at 9600 baud by default.
Yeah, we did that, but we don't get an address.
So we haven't checked for that.
Good point. Try plugging it in to the other Ethernet port at the base. I should mention, we are running on a hope and a prayer here because Capital Factory provided us with one Ethernet jack and said down there it's one of these. So we're going to try plugging into a different one, restarting the router, and see if we get addresses real quick. Sorry about that.
Oh, so nobody's getting that.
If you're not using it.
We're all going to hammer the DHCP server at the same time.
So you should.
That's why they were putting
Oh, you mean this is a driver until our device. I think that's what they
I'm going to cover something before. Okay, now what? Do me a favor, I can't read you. Is it just
But I'm not able to see don't say too much. This is complicated, but I don't know.
Yeah, really.
So what do we do actually?
Bear with me 1 second. We found out that back there we're having an issue with the DHCP server. Give me 3 minutes to sort it out. We've kind of got this daisy chain going on around the room where we're connecting this giant U shape all back to a single port and a bunch of switches. So it's supposed to be working. I tested it earlier and it was working, and now it's not. 1 second. Okay, so it seems like everybody's just about done it. It seems like everything's working except the TV. There we go. So does anyone have any questions on TCP and UDP other than why did it crash at first? No? Cool. Everyone feel comfortable with TCP and UDP? Come on, guys, you hear me some feedback here. I'm not a mind.
Yeah, we feel comfortable with downloading the programs and putting passwords in.
All right, cool, thanks.
Wait, what was the whole point about TCP versus UDP being reliable or not?
Right, so you walked in about halfway through that. I'm going to review that for you real quick. Here's the difference between TCP and UDP. TCP is a connection-based protocol. UDP is connectionless. That means guaranteed versus non-guaranteed delivery. That's really it. UDP is more like a fire hose. TCP is more like a nice, proper British conversation.
Yeah. So why use UDP over TCP?
Or streams. UDP is used for streams and high bandwidth stuff. You don't care if all of it gets to the endpoint, like streaming video data or audio data, where you can correct using an algorithm for what's missing. TCP is used for other things. You'll see most security protocols are based off of TCP because there's a guarantee of transmission. It's not to say there isn't security in UDP. There is a thing that does that. But you'll see that most of them are TCP based.
Is IoT on one side or the other?
It spans all of it.
Should also say that streams are best when, if the data packet is missing, it's best to forget it.
Yes, correct.
That's the way
You don't want to try and you don't want
You
to
don't want to get it again. You've lost it, it's too late. Audio, video, stuff like that.
So, now that we've covered TCP and UDP, we are at the end of what I planned, but we still have about 30 minutes of time left. Does anyone want to try and cover a little bit of protocol overview, or do you want to just leave that for next time?
Yes.
Cover? All right, no one's saying no, so I'm just going to go ahead and dive in. Forewarning, there are no examples for these today, because the examples are just as in-depth as what we just went through. So today I'm just going to give you an overview of a couple of protocols. We'll have examples for them next month, and we'll also have more protocols next month. This is me being an overachiever and trying to get it done a month ahead of time, and I'm really glad I did it. So we're going to review two protocols today, HTTP and WebSockets. Who here has heard of HTTP? Okay, who are the Luddites who haven't heard of HTTP? Like if you use the internet, you have to type HTTP ... And who's heard of WebSockets? WebSockets? I'm not surprised to hear that. So HTTP. It is HTTP ... then an address. That denotes that you're using the HTTP protocol shooting at some server address and then some resource on that server. This is the same for any protocol used on the internet. Whether it be HTTP, HTTPS, which is a secure version, Gopher, if anyone was around when Gopher was a thing. Yeah, you know some. WebSockets is ws.//
Better's finger.
I haven't heard that one in a while. Every protocol across the internet starts out with a little thing ... HTTP is HTTP. So pros and cons. Not really cons, more like this is what HTTP is, take it as it is. It is TCP based, it is not UDP based, so it has a guarantee of delivery. It is widely used. When you think the internet, you probably think HTTP. Yeah? Like when you think the internet, you probably think a website. It's all HTTP. Big benefit is it is stateless, which means once you've got a connection open and done, you don't have to worry about what came before it or what's coming next to influence your decision. It's just, I've got the thing and I'm done. You request it, you receive it, you close the connection. That's how HTTP works, totally stateless.
It's a file transfer protocol.
Thank you, sir. Downsides, it's kind of bulky. This is not an inherent implementation of HTTP. It's more like the most common use case of UDP is bulky. That is to say websites, primarily ASCII data, where each character is 1 byte. So even the most basic web page, if you open it up, it's going to be 800 kilobytes is the smallest web page I've ever seen, and they go up to a couple of megabytes. If you look at that blue board that you've got on your desk, that thing has got a meg, 1 single meg of flash memory. On average, 1/8 to 1/4 of that is used up by the program that you loaded on it, and then there's some more stuff at the end, and then there's this nice chunk in the middle, so on average you've got about 1/2 megabyte at the most that you can fill up with data. So if you're going to request a web page, it can be 1/2 meg at the biggest, and then you're totally out of data, you crash. You overflow your stack or your heap, and you're out of luck. So it's probably not the best idea to try and load a web page on a microcontroller is what I'm getting at here. That said, HTTP is slightly quirky depending on what server you're talking to. Some servers enforce HTTP 1.0, some enforce 1.1, some enforce 2.0. Some, if you're talking to a Google server, will try and enforce /2, not to be confused with 2.0. They do this awesome thing with TCP. Anyways, the point is each HTTP implementation between Node.js and Apache Tomcat have their own slight little quirks, especially if you're dealing with, say, there's a common one for the Windows server, where some of the headers are different by 1 character in the header naming. And so if you're in an embedded system and you're incredibly pedantic saying it must be this header name, it's off by 1 character, you can't recognize it. So that's the kind of stuff that you'll run into. The other downside is every resource is a new connection. To help visualize that, this is the socket lifetime of a HTTP connection. The client sends a request to the server. The server sends a response back to the client. And the client goes, yeah, I got it, don't worry about it, we can close it down. Again, TCP, so it is guaranteed transmission, and it's acknowledged. The thing to note is the thing underneath request and response. When you request, you send across a request type and some headers, and maybe a payload. That type, if you've ever dealt with HTTP, is stuff like post and get and delete. They're HTTP commands. The headers are kind of like metadata about what you're sending across. If I were asking for a web page, for example, I'd send across a GET request. I want to get that web page, and I send across the server name and maybe the index.html file that I want. The server would then respond with probably, well, hopefully, a 200. Would respond with the 200 status for it is okay. Here's your thing. Everything's golden. It would then have some headers saying here's some cookies associated with it, here's the timestamp, here's the server name, and then it would have a payload that would be the binary representation of the website, again, in ASCII. So just to refresh, you have a request with a request line, request headers and a payload. You've got receive that comes back from the server. There's a status line, some response headers, and then a payload if it applies. I see a lot of people yawning, which means some people are having trouble. Hit me with questions. What do you got?
What happens if keep alive doesn't close it?
Right. So remember how TCP closes? Keep alive is a hack of TCP where there's usually a timeout associated with the TCP connection, and if nothing is sent before that timeout happens, it automatically closes. Keep alive is a special header that can be set so that you ping out just before that expiration period. So if you say keep alive at 1500, usually 1500 milliseconds, so about a second and a half, then at 1499, you'll send a packet out just to keep the connection open. And usually you'll send like a new line or something, and the server will just be like, yeah, trash data, but we're keeping the connection alive. Other questions? All right, I'm going to show you an example. This is an example of a GET packet, so a GET request packet, and a GET response packet. It should be broken up into 3 distinct sections. The first one on the request is GET, which specifies the type of request. It's also specifying it's using HTTP 1.1. There are some pretty major differences between 1.0, 1.1, and 2.0. They will involve what order things come back in, what header types are available, things like that. In general, the majority of the web runs off of 1.1, so if you write to 1.1, you're probably safe. So that's what I'm showing. You'll notice that there's no payload in the request, because a GET request does not send a payload. It just sends a GET request, which is the GET. That thing right there, it says GET. If you were sending a POST request, you would have a payload here, which would be the payload data for the POST request. Has anyone ever looked in, say, a web page when they're visiting and seen like a question mark Q equals blob of data, ampersand, R equals whatever? Have you all seen that?
PHP.
Not PHP, it's a query, but yeah, you'll see that. That is a GET request. GET requests and data transmission are sent as key value pairs in the URL bar. It's totally public. Anyone sitting on the internet can grab that data, assuming you're not on a VPN or super encrypted or anything else. If you're just using the internet, a GET request is totally out in the open. So don't try and use it for anything secure. On the other hand, a POST request will take that data, instead of putting it in the bar and having it in, sending it across in here, it'll be sent in the payload. And you can do things with security to ensure that that payload is secure and no one can sniff it. So GET unsecure, POST more secure. Still have to make sure you're doing actual security underneath the sheets to make sure no one hacks into it. The response packet for this GET packet, if you notice it says HTTP 1.1, status of 200, okay, that just means the server is good to go. If it replied with 404, that's an error. 500, that's an error. 401, 402, these are all error codes that the server will respond with. You've probably seen them when you tried to hit a web page and said error 404 not found. That's the server response code, is 404. Then it replies with a bunch of data about the web page, and then the payload, it replies with the HTML of the web page itself. Does anyone have any questions?
Are you saying that there's other ways of protecting your payload other than using an HTTPS connection? Can you do that over straight HTTP?
There's a million and one ways to do security, and that's a whole other talk that I'm not qualified to give. HTTPS is the most common form, which is just a wrapper at HTTP that adds security in its own way. You can add TLS to things, DTLS. There's all kinds of different versions of security. There are even certain protocols that will use a PGP key to encrypt the payload before sending it, send it across regular HTTP, and then decrypt it on the other side because there's a prearranged agreement. So security, I'm just not going to touch it because I could be here all night. But yes, there's more than HTTP that you can do to secure your payload. especially if you control it at the embedded system level, where you're manually setting the payload. So you could just as well encrypt it with your private key or something like that.
So you would encrypt it using your private key and then just send it over a HTTP connection?
That's just one way that you could do it. I'm not saying that's standard. Since we're talking about standard protocols tonight, I'm going to say at some point in the future I will give a security talk. Because I don't want to recommend non-standard or non-good practices.
Also, the CPU may not be strong enough to handle encryption bills.
Exactly. So that was HTTP. Again, no examples this month. Next month, we'll have a HTTP client example. You'll hook up to stuff and talk to things on the internet, assuming we can set all this up again and not have huge bugs. WebSockets, they're another protocol. They use WS//. This was a thing that came about, what was that, 2010, 2012? It's a relatively new thing. It's essentially a way to open up a pipe across TCP. So if you remember, you were talking about Keep Alive. TCP closes after a timeout or after the data has been sent. Once you've got your thing, the connection's done. You don't send multiple things across that connection. WebSockets are a way of doing that, keeping the connection alive and turning it into a true pipe to just shove stuff back and forth. The standard implementation of WebSockets happens on port 80, so it gets through most firewalls and most militarized zones on web servers. So you can usually use it on existing infrastructure. It is a server-to-client infrastructure, so it has a centralized server, and all the clients talk through it. Other big perk, all the major browsers support it. Firefox, Chrome, Internet Explorer, and Opera all have support for WebSockets. So you can use this on your computer, you can use it on your embedded system, and any server that you're going to use, unless you wrote it yourself in college, is going to support WebSockets. The other really cool part about it is because they did it in TCP, and because of some of the really cool hacks they put in place, well, not hacks, just really awesome coding they put in place, it is real time, or at least as darn near real time as you're going to get across the open internet. That means you're not going to have minute-long lags. You're going to have real-time data plus or minus about a quarter second in most trials. This means that you can enable things like maps. There's a whole bunch of real-time map applications that use WebSockets to talk to their server because they can shove location data up and get the map file back in real time. Downsides, not so much downsides as they are constraints really. Each WebSocket connection does use a single TCP socket, which means you can only have one per port. So if you're going to have one and you're going to use it with a server, each device needs its own socket on the server. So that's fine if you're doing less than about 10,000 devices. I can run 1,000 WebSockets on this laptop just fine. If I try and go beyond that, I'm going to start having issues with my machine running out of sockets or running out of resources because each device you add is a linear amount. There is no built-in ability to manage multiple connections from a single socket like you have with some pub/sub architectures. The other downside is there is slightly inconsistent support. Because you have Internet Explorer, Firefox, and Chrome, and Opera all supporting it, of course they all support it in different phases, at different revs, and to a different extent. So while there is a core of about 90% that is absolutely universally supported, there are edge cases where you'll run into an issue with Chrome doing one thing, but Firefox does another. So you just have to be aware of that. To be honest, I don't know of any protocol where this isn't true. It's just particularly true with WebSockets. And it does require a dedicated server. So it is not distributed, it is a client-server architecture. So if you want to talk to another client, you have to go through a server.
Question.
Yeah.
Does that mean that it's mutually exclusive with my Apache server?
Can you rephrase the question? I don't quite understand.
Can my Apache server that's on port 80, can it also receive incoming WebSockets requests?
I don't think so. No. Requires its own port. One WebSocket connection, one port on the server. So if you want to serve a web server, your web server is bound to port 80 and it accepts web connections, not WebSocket connections. So HTTP. Okay. Anybody else?
So what about the chip we're using? What would be an example of, can you use a WebSocket with that, with XPro?
Yes. So there is a WebSocket example for that chip, actually. Well, actually, it's an embed WebSocket example. So any embed board that can connect to the internet because that Berkeley socket abstraction. This is a great point. Thank you for that. Remember way back in the beginning where we had layers 5 through 7 and layers 4 through 1, and applications were up here and hardware was down here? HTTP, WebSockets, these are all application level. They don't care what your hardware is because they talk Berkeley socket down, and then the Ethernet interface talks Berkeley socket. So when it says TCP open, this thing goes, oh, TCP open, I can do that. By the way, here's some TCP received data. Oh, thanks, you gave me the data I want. I can easily switch out that Ethernet interface for a Wi-Fi interface and say TCP opens, oh yeah, I know how to handle it, I got that. And take it and then hand stuff back and it catches it. So because of that Berkeley socket API, it doesn't matter what hardware you run it on as long as it speaks that API. So there are WebSocket application examples, and they do work. There is no WebSocket server set up currently. The reason I kicked the examples to next month is because I need to go bring it back up because it went down and I lost the code for it, so I got to go redo that. So next month I'll have that up and running for you. If you're interested though, look at WebSockets on the embed website. There is a way to implement them locally using Eclipse and some Java code. So if you wanted to, you could run a local WebSocket server and connect it from your board.
Cool.
Yeah. Go be awesome and come back next month and show me what you did. Okay. Or don't, and I'll show you next month. Sorry, there was another question, wasn't there?
Yeah, I was curious. I've seen port 80 and I've seen port 8080.
Yeah.
What's the difference, or why do people use one over the other?
Oh, good God. If I remember correctly, port 80 is the traditional web server socket. So that's what web usually goes across. 8080 is also associated with it. Maybe, David, you know why they shifted to 8080?
Because it was convenient to type 8080.
Yeah, it's easier to remember.
It's just
There you
easier
go.
to remember.
I know
Only reason.
they're both open by default on most firewalls unless you explicitly lock them down. I know they're both web associated. Beyond that,
IP ports below 1024 are defined. Above 1024, it's open season. And you have 65,000 of them, so.
So actually, some of those are both 1024 and defined too. It just says getting root privileges to open ports below 1024, but you don't above 1024.
there you go. I learned something tonight.
Yeah, MQTT, for example, has one defined that's up there.
We're going to cover that next month, by the way.
Yeah, I do a lot of
My SQL 1366?
Yeah, and I think it's different.
So this is what a WebSocket handshake looks like. You notice those red arrows, they actually start out life as an HTTP connection. Then there's this neat little upgraded process that's essentially a secret key where they go, hey, WebSocket, WebSocket, okay, WebSocket time. And they start up as a WebSocket. At that point, you get a pipe open to both ends, and you just say WebSocket send, WebSocket receive, WebSocket send, WebSocket receive, back and forth all day long until one of you wants to close it, and then someone closes it, and the connection falls down. So either side can close the connection as they see fit, as resources run out, whatever.
Good socket IO implementations will reconnect if it was an intermittent.
Okay. I'll actually talk about socket IO. I think in the third class is what I got that scheduled for. So that's all I've got for you today. If you want to be really enterprising, there are examples that exist for HTTP and WebSockets. I can't guarantee they work because I haven't checked them yet. So by next month, I'll guarantee they all work.
The MQT example doesn't work.
And we'll see what guarantee that works.
It doesn't know what compiles of errors.
Talk to you later about it.
I'm trying to fix it.
Yes, think about that. So one thing I want to ask you though, we do have a feedback form. It's how I validate my existence and validate it to my superiors to be that I deserve money for pizza and beer. So if y'all wouldn't mind filling that out and telling me what you need, what you want, what you like, what you hate, it helps me get free pizza and beer. So here we go.
Yay.
Aside from that, next month we're going to cover some Wi-Fi. So we're going to keep on the protocols for the web. We're also going to touch Wi-Fi using an ESP chip. If none of you are familiar, ESP 8266 is in quantity or just straight from China, a $2 to $3 Wi-Fi chip that talks over serial. You can order it from Amazon Prime for about $8 with 2-day delivery if you like. I'm going to be posting here in about an hour what the next meetup will be, what we're going to cover. Everyone will need to buy their own ESP chip. I'm going to bring these boards back, and we'll have shields, and everything will be dandy.
I tried the URL, it doesn't seem to work.
It's an L, lowercase L.
Oh, it's an L? Yeah, that's an L.
LB.
Sorry about that, guys. My ones are always like the fancy 3-stroke ones.
I mean, some.
Can you tell us more about the chip? I'm sorry. What chip was that? I'm sorry.
It's the 8266.
So in about an hour, I'm going to post the next meetup, and all the stuff you'll need is on there. Just make sure to bring your laptop next month, buy an ESP chip, come back. Before you leave, fill out the form. And if I could get everyone to help me clean up, because it took me a while to set up all these Ethernet cables, pull your Ethernet cable, wrap it up for me, and do a little twisty thing so it doesn't fall apart. Put your board back in the box, wrap up the USB cable, and just set them all on top of each other. And that really helped me out and get me out of here before midnight. Yeah.